Hi everyone, in this video we are going to go through L5. So we're going to be discussing functional groups. So remember, when we talk about functional groups, what we could potentially see is called an aldehyde. So this is what an aldehyde looks like. It's got that C double bonded O and it has that H group coming off of it. Whenever we name aldehydes, our ending is -ale. So we're still going to find that longest chain. And then instead of writing "ane" at the end or "ene," we write "al." So in this circumstance, we have two carbons. So that would be ethane normally. But instead of writing ethane, we write ethanal. Let's go up to this one here. So this question's a ball and stick figure question. We're going to start this guy as carbon 1, 2, 3, 4, 5. And the aldehyde will always take precedence or take kind of that number one responsibility. So this is going to be pentane normally, but again, because of the fact that we have an aldehyde, we're going to write pentanal. And we don't have to put a 1 out in front in this circumstance here. It's automatically assumed. All right, same thing here. Again, we'll do our longest chain, 1, 2, 3. And because we have an aldehyde, this will be prop. And for the 3 carbons, ale. All right, next we're going to talk about ketones. And when we discuss the idea of ketones, we're going to write "-one". Now remember, when you see a ketone, it looks something like this. And so we can see this in ring-like format. We can see these as long, crazy chains. Here, we're going to make this ring-like format. So again, we're going to make that ketone number 1, 2, 3, 4, 5, 6. So this will be hexane. And because again, it's going to be a ketone, we write "-one". Now, because this is a ring-like format, don't forget to write cyclohexanone. All right, same thing here. We're going to have to write that we have 1, 2, 3, 4, 5. Longest chain is going to be penta. And then again, because it's going to be a ketone, we write "-one". Now we want to write where that carbonyl group is, this guy here, because it's not on the 1. So we want to make sure that we write 2, pentanone. But then we also have this methyl group to account for on the 3rd carbon. So we're going to write 3-methyl-2-pentanone. All right, same thing here. Longest chain, 1, 2, 3, 4, 5. And we have that carbonyl on the 2nd carbon. So this is going to be 2-pentanone. All right. Next question, what we're going to do is we're going to start drawing these aldehydes and ketones out. So we have 5-hydroxyhexanal. So sort of work your way backwards. We know that hex is 6, so we're going to have to draw out 6 carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we know we have that hexanal. So we're going to make this a C double bonded O, and it already shows that hydrogen. So that's going to be our alkane. That's going to go on number 1 unless it says something different. So it's on the 1st carbon. Then we have this 5-hydroxy that we have to take into account. Hydroxy is going to be an OH group. So, and that's going to be considered on the 5th carbon. So we have 5-hydroxyhexanal. All right, next one is going to be 3-methyl-benzaldehyde. So benz is a benzene ring. It's an alternating ring of single and double bonds. And what's going to happen is we're going to claim this guy is carbon 1, and we're going to stick out that aldehyde here. It's not going to sit on the actual benzene ring. It's going to be sitting out here like this. So we have the benz, and then we have the aldehyde. And now what we have to do is we just have to take into account that methyl group. So we're going to call this carbon 1, carbon 2, carbon 3. So we have 3 methyl benzaldehyde. All right, and last but not least, we're going to do 3 hexanone. So 6 carbons like this. On the third one, we have that ketone. So this is going to be 3 hexanone. Next, what we're going to do is we're going to discuss the idea of solubility and boiling points. So when we discuss solubility, the aldehydes and the ketones are going to be more soluble than just a straight chain alkane. So if you were to look at 2-butanone, a ketone, that's going to be more soluble in water than pentane, the straight chain 5-carbon chain. So we'll submit our answer. And then next, we're going to be caring about the idea of increasing in boiling point. So what's going to happen is as you add on oxygen, nitrogen, those very electronegative components, it's going to increase in molecular forces and it's going to increase in hydrogen bonding. Because of that, it's going to increase the boiling point. So just a straight chain alkane, again, carbons and hydrogens, that's going to have a low boiling point. But then what's going to happen is we're going to see with alcohols and these aldehydes, they're going to have an increasing in boiling point because, again, they're able to have those molecular forces. And alcohols are going to have a higher boiling point than ketones or aldehydes. So this guy will be the highest, and this guy is the intermediate. And last but not least, again, thinking about solubility, hexane is a 6-carbon straight chain. 3-pentanone has that ketone group associated with it. So hexane is going to be less soluble in water than 3-pentanone. All right, next couple that we're going to see are going to be reactions. So what I've done for you guys is I've posted a link, and you can see this under your Module 5 content. I've linked a couple different types of reactions to look at, and one of them is oxidation, and one of them is talking about something called this addition using H2. What's going to happen here is we're basically going to be either converting from a ketone to an aldehyde to a carboxylic acid, or an alcohol to an aldehyde. With oxidation, oxidation is loss of electrons, but you gain bonds to oxygen. So what's going to happen here is when you have this aldehyde, it's going to lose this hydrogen, and it's actually going to gain a bond to oxygen while this is happening. So we're going to draw out this picture. And we're going to see C double bonded O. And it's going to look something like this. So instead of having an aldehyde, we're going to have what's called a carboxylic acid. C double bonded O, OH group. All right, next one is the same idea. We're going to be dealing with ethanal, which is going to be an aldehyde. And we're going to see what happens when it reacts with the Tollens reagent. So we're going to draw out our ethanal. And that way you can kind of see what it looks like. Now, what's going to happen here is when this reaction takes place, instead of it looking like OH, it actually loses that additional hydrogen. So we're going to have to put some lone pairs, or we're going to have to put like a plus or minus sign around this guy. In this circumstance, because it lost that hydrogen, it's going to have a minus sign associated with it. So this is what it looks like to be oxidized. And then same thing here, we're going to complete the following reaction. And what's going to happen here is we're going to be adding on hydrogens. When we add on hydrogens, we're going to lose bonds to oxygen. So here we have a ketone that we're starting off with. Oopsie. Fix that. So it looks something like this normally. And what's going to end up happening here is we're going to lose that double bond. And it's going to now be an alcohol group instead of a ketone. So ketones are going to be reduced to alcohols. Alcohols can be oxidized to ketones, and then they can be oxidized to aldehydes or carboxylic acids. All right. This one says, draw the formula for the product formed when 3-methyl-2-butanone is reduced. So same thing, we're going to be dealing with a ketone, and we're going to now make it into an alcohol. So we'll draw this out. Butanone, 4 carbons. It says that carbonyl is on the second, so we look something like this. And then again, we have that 3-methyl coming off. And like I said, this guy will end up being reduced down to an alcohol. And this says, complete the following reaction by writing the name of the product. So again, here what we're dealing with is cyclopentanone. What's going to end up happening is we're going to now have an alcohol group. So instead of having cyclopentanone, we're going to end up with this alcohol. So this will be 1-hydroxy and, or actually it'll be cyclopentanol. So when you have an alcohol, it ends up with an OL at the end. Aldehyde will have an AL. So this is going to be called cyclopentanol instead of cyclopentanone because it became an alcohol. All right, we're going to start practicing writing more IUPAC namings. This is going to be for our carboxylic acid. So for our carboxylic acid, again, that'll be this. It's a C double bonded O, OH group coming off of it. And what's going to happen is, again, we're going to start with the longest carbon chain. Start with this as number 1, 2, 3, 4. Just like we would before, 4 is going to be bute. And what's going to happen here with carboxylic acid is we're going to end with oic acid. So oic acid. And then we just state that on that second carbon, we have a 2-methyl-butanoic acid. All right, let's do the next one. So we have 1, 2. So again, ethane normally, but this is going to be ethanoic acid. And same thing here. We're going to end up writing this piece out. Now this guy is a little bit funny because now we actually have 2 carboxylic acids. So we're going to have to take that into account. Now this one's a little bit funny because you have 1, 2, 3, 4 carbon groups. And on the carbon groups, you'll see that there's 2 carboxylic acids. So we're going to name this one a little bit different. It's going to take that butane. Let me do this in dark. It's going to have that butane associated with it. And again, we're going to have this oic acid associated with it. But we're first going to write butane. And because there's 2, we're going to write di-oic acid. So this is, we don't have to write out that it's 1,4. We'll say butane dioic acid to name this carbon group. All right, moving on to the next one. All right, we're going to draw the structural formula for ethanoic acid. Ethano tells us that we have 2 for ethane. Oic acid tells us we have a carboxylic acid. So we'll have that C double bonded O, OH group coming off. Submit our answer. We're good to go. All right, this one's the same, the ethanoic acid, but this one's going to be a little bit different. So we're going to start off with the butanoic acid that we'll see here. And then it tells us that we have 2,3-dimethyl. And again, we're going to make this one number 1. So we're going to put that OH group. And that's C double bond O, OH group. And we are good to go. Okay, this wants us to understand the idea of basically these properties of carboxylic acids. So again, when we're dealing with the circumstance here, we're thinking about boiling point, and again, we start thinking about polarity and those intermolecular forces. So carboxylic acids are going to actually have the highest boiling point. The OH group would have the intermediate, and again, the aldehyde would have the lowest boiling point. Again, same thing, thinking about increasing. The carboxylic acid would have the highest. The lowest would be that straight chain alkane, and then intermediate would be that aldehyde. All right, and same thing here, carboxylic acid would have the highest, lowest is the alkane, intermediate would be the aldehyde. All right, next what we're going to do is we're going to classify these amines as primary, secondary, or tertiary. And when we discuss the idea of primary, secondary, or tertiary, you're thinking about how many carbons are actually attached to that nitrogen. So for this first guy here, this straight chain, if you were to draw this out, it would look something like this. So there's only one carbon attached to that nitrogen. So this is a primary. This guy here, again, the way we see it, this is a carbon, there's a nitrogen, and then there's another carbon. So this would be secondary. And what this guy is kind of attempting to show you, but we have to kind of state it out a little bit. Again, you got that benzene ring. Because remember, that's carbon, nitrogen. And this is saying that it looks like this. That's why we see it in those parentheses to show that there's 2 of them. So this guy would be considered a tertiary amine. All right, same thing. We want to think primary, secondary, tertiary. This nitrogen would have 2 attached to it. So that's going to be secondary. This nitrogen also has 2 attached to it, secondary. And this guy would only have 1. So this guy would be primary. Last but not least, again, only 1 nitrogen carbon attachment, primary. Only 1 here, primary. And only 1 here, primary. They made that one very easy. All right, next what we're going to do is we're going to actually start naming and drawing structural formulas for these amines. And what's going to happen here is the amine is actually going to be in the middle. And what's going to happen is it says diethyl-methylamine. So there are 2 ethyls here and here coming off of it. And then it says that there is a methyl group. So it looks something like this. So 2 ethyls, 1 methyl, they're all attached to that nitrogen. So it's diethyl-methylamine. All right, this one says triethylamine. So again, in the middle, you'd have your nitrogen, and you're going to just have 3 methyl groups coming off of it, like this. All right, this says diisopropylamine. So again, same thing. You have this, and then we just draw those isopropyls. That. Nope, we don't want that double bond. We want it to look something like this. All right, so drawing those and naming amines are actually relatively pretty easy. All right, same thing, we're going to make sure that we write our amine. So it says that we have 1 hexanamine. So again, 6 carbon chain. 1, 2, 3, 4, 5, 6. And off the first carbon, we have the nitrogen. So 1 hexanamine. All right, same thing, butanamine, 4 carbon chain. Make sure you have 4 carbons. And off that first carbon, we have the nitrogen. Second one, same idea. Propanamine, 3 off that first carbon. We have that nitrogen. All right,